Podcast 1, Eddy Current Without the Magic. From welding engineer to eddy current inspector, welcome to Podcast 1 of our Eddy Current series. The goal of this lesson is simple. By the time you finish listening, you should understand what eddy current testing actually is, what it is measuring, why it works, and why it's complicated. If you have ever sat through an NDT course and felt like the instructor was trying to summon spirits through an impedance plane display, this lesson is for you. We're going to strip away the jargon and build this from the ground up. As we go, I'm going to assume you're an engineer, inspector, welding professional, or somebody who already understands how technical systems work. I am not going to talk to you like a first semester college student. Instead, we're going to connect eddy current testing to concepts you already understand. What problem is eddy current trying to solve? Let's start there. Every NDT method exists because we need to answer a question. Visual testing asks, can I see a problem? Liquid penetrant asks, is there a crack open to the surface? Magnetic particle asks, is there a surface or near-surface discontinuity in a ferromagnetic material? Ultrasonic asks, can I bounce sound through the... Radiography asks, can I see density changes through the thickness? Eddy current asks a different question. It asks, can I detect changes in a conductive material by observing how electricity behaves inside that material? That's it. That's the entire method. Everything else is details. Eddy current is really an electrical method. One of the biggest mistakes people make is thinking eddy current is a magnetic method. It isn't. It uses magnetic fields, but ultimately it is an electrical method. Think about it. We put alternating current into a coil. That current creates a magnetic field. That magnetic field induces electrical currents inside the material. Those currents respond to the material. Then we measure how those currents changed. The whole thing begins and ends with electricity. The magnetic field is simply the messenger. The pond analogy. Let's build a mental picture. Imagine a still pond. You throw a rock into the water. Ripples move outward. Now imagine the pond contains logs, weeds, rocks, and obstacles. The ripples change. Some reflect, some weaken, some distort. Now imagine you're blindfolded. You cannot see the pond, but you can measure the ripples. From those ripple changes, you can infer what is beneath the surface. The magnetic field creates the disturbance. The material responds. We observe the response. What is an eddy current? An eddy current is simply a circulating electrical current induced inside a conductor by a changing magnetic field. As from water. Think about a whirlpool. Think about a swirl behind a rock in a stream. The current circulates, it loops, it spins. Electrical eddy currents do exactly the same thing. They form circular current paths inside the metal. Why alternating current? Good question. Why not use DC? Because nothing changes with DC. No changing magnetic field, no induced current, no eddy currents. Change. Alternating current constantly changes direction. The changing current creates a changing magnetic field. The changing magnetic field creates eddy currents. No AC, no ET. Simple. Primary field and secondary field. You'll hear these terms constantly. Let's simplify them. The probe coil generates a magnetic field. When that field and currents are generated, those eddy currents create their own magnetic field. That's the secondary field. The secondary field opposes the primary equally from Lenz's law. The induced current always fights the thing that created it. Remember that. Induced current is stubborn. It resists change. Always. Always. Lenz's law for welders. Forget the textbook. Here's the practical version. Every time you try to shove energy into a conductor, the conductor pushes back. That pushback is what we're measuring. That's really what ET is. We're measuring how hard the material pushes back. Different materials push back differently. Cracks push back differently. Corrosion pushes back differently. Heat treatment pushes back differently. Conductivity pushes back differently. Everything becomes a change in pushback. What happens when a crack appears? Imagine eddy currents flowing through aluminum. Everything is smooth. Life is good. Then they encounter a crack. The current cannot jump across air. The flow path changes. The eddy currents must move around the crack. The current density changes. The secondary field changes. The probe sees the change. The instrument displays the change. The inspector sees an indication, never sees the crack. The instrument only sees disturbed current flow. That is a critical idea. ET never detects cracks directly. ET detects the effect cracks have on electrical current. Why ET works so well on aircraft? Aircraft are loaded with aluminum. Aluminum is conductive. Aluminum is non-conductive. Aluminum is non-ferromagnetic. Aluminum has predictable properties. This makes it nearly ideal for ET. That is one reason ET became so important in aerospace. Aircraft structures accumulate fatigue cracks. Fastener holes crack, lap joints crack, skin panels crack. Many of those cracks begin at or near the surface. That is exactly where ET shines. File site turn file 111. Why steel is more difficile introduces another variable, magnetic permeability. Suddenly the signal is responding not only to conductivity but also magnetic behavior. The inspector now has multiple competing influences, permeability changes, material variations, heat treatment differences. All of these can influence the signal. The signal becomes harder to interpret. This is why many ET, you hand them an aluminum part and sigh when you hand them a steel one. What are we actually measuring? This is where many students get lost. The answer is impedance, not conductivity, not corrosion, impedance. Everything eventually becomes an impedance change. If you're an engineer, think of impedance as AC resistance. Not exactly resistance or now. Impedance combines resistance and reactance. The ET instrument is measuring changes in coil impedance. The material changes, the impedance changes, the impedance changes. The instrument reports the change. Why reference standards matter. This is probably the most important practical lesson in ET. ET is fundamentally a comparison method. You compare one condition against another. Good part versus questionable part. Known flaw versus unintended versus inspection article. Everything starts with a reference. Garbage reference, garbage inspection. Perfect instrument, bad reference, still a bad inspection. The reference controls everything. Think like a welder. Let's compare this to welding. Suppose I ask, is this weld acceptable? You ask, compare I 1104, acceptance criteria matter, reference matters, context matters. Same thing here. An ET instrument by itself is useless. The instrument only becomes meaningful when connected to a known standard. The importance of calibration. Many ET failures are not equipment failures. They're setup failures. Poor calibration, poor standards, poor scanning, wrong frequency, wrong probe. The instrument is often working perfectly, the inspector isn't. This is one reason experienced level 2s obsess over setup, because setup determines everything that follows. ET is a signal-to-noise game. Let's introduce another concept, signal versus noise. Signal versus noise. The flaw creates signal, everything else creates noise. Probe wobble, surface roughness, edges, geometry, fasteners, paint, temperature, material variation, all noise. The inspector's job is separating signal from noise. That's the real profession, not operating the instrument. Why ET feels like magic. Many newcomers feel ET is black magic. Why? Because they jump directly into displays. They start looking at impedance planes, phase angles, filters, complex traces. They never learn what the machine is actually doing. Imagine teaching welding by starting with welding procedure qualifications and Sharpie testing. Nobody would understand anything. Instead, we start with, this is an arc. This is molten metal. This is shielding gas. Same approach here. This is a coil. This is a magnetic field. This is induced current. This is what a crack does. Everything else comes later. The 4 big variables. As we move into later pods, you'll discover almost every ET indication is driven by 4 major variables: conductivity, permeability, geometry, distance between probe and part. That's it. Most signals are some combination of those 4. Understanding those 4 variables is the difference between guessing and actually knowing what you're looking at. The mental model of eddy current. Here's the model I want you to remember. A coil produces a magnetic field. The magnetic field creates eddy currents. The eddy currents create a secondary magnetic field. Material properties affect the eddy currents. Changes in eddy currents affect impedance. As impedance changes, the inspector interprets those changes. That is ET. Everything else is refinement. Closing thoughts. If you remember nothing else from today's lesson, remember these 5 ideas. Number 1, eddy current is fundamentally an electrical method. Number 2, the instrument never detects cracks directly, detects disturbances in current flow. Number 3, everything eventually becomes an impedance change. Number 4, ET is a comparison method. Good standards equal good inspections. Number 5, the entire profession is really signal discrimination, separating meaningful indications from meaningless indications. In the next lesson, we're going to tackle conductivity and permeability. That is where ET starts becoming useful, because once you understand conductivity and permeability, frequency selection, depth of penetration, crack detection, conductivity testing, alloy sorting, and heat treatment verification, all making sense. And that is when ET stops being magic